Ladies, gentlemen, and gender transcenders, would you please welcome your keynote speaker for this afternoon, Rendle, because apparently I have to do it myself. Thank you very much. This is a 1 hour talk. I've got 30 minutes. So I'm going to talk fast and then record it and then play it back at half speed. And it'll be fine. So yes, I'm rendle.dev on Blue Sky. Not really on any other social networks except LinkedIn. Is that a social network? I don't know. So yes, I am old and I have been doing this for a very long time, 35 years now. This was the first computer I worked on. A Tandon 286 with 2 megabytes of RAM, 150 megabytes of hard disk, and 8 programmers working on it. And we would code all through the morning from 9 until 1, and then we would start the build, and then we would play table tennis. We would play ping pong for about 2 hours while the build ran. And if you broke the build, you were the one who had to stay and fix it and run it again overnight. So yes, it had an Intel 8286 processor, 8 megahertz, thousands of hertz. It had 1 core, 134,000 transistors that you could actually see if you looked at the chip with a magnifying glass, and no floating point or anything like that. So Moore's law says that the number of transistors doubles every 2 years. I think it's 18 months, 2 years, whatever it might be. So now, the current sort of state of the art is the Apple M4 Max processor, which has runs at 4 gigahertz, so it's like, what's that, 500 times faster than the 286. It's got 72 cores if you count all the NPUs and GPUs and CPUs and efficiency and performance. It's got 100 billion transistors. They haven't released the actual count, but it's going to be upwards of 100 billion transistors. It's a 3 nanometer process, okay? Just to give you an idea of what that means, if that's a 1.5 micrometer transistor and we shrink it down like this, then it becomes, oh, it's that small. It's that, there is actually a pixel here, okay? And this one, I swear to God, is sized so that that is the correct ratio between those two things. It's there, you see? We had 2 megabytes of RAM, and it was DRAM. It was this kind of sim thing. It ran at 22 megahertz, and it could do 0.017 giga transfers per second, which is what we now measure memory performance in, because now we have things like DDR5 8800, which does 8.8 giga transfers per second, 70.4 gigabytes per second transfer rate. This was the hard disk. Does anyone remember 5.25 inch full height SCSI drives? They were monsters. If you dropped one on your foot, that was a trip to the hospital, okay? These things were heavy, and that was 150 megabytes that we could fit on there. And so that's a London bus for scale. And now, we actually have Samsung do a 4 terabyte micro SD card. So the size of your fingernail, 4 terabytes of storage. And yeah, that's roughly the kind of size ratio for those two things. I had a Wyse 50 terminal. It was 80 by 24 characters, didn't do graphics unless you used curses to do the weird line sort of ASCII code set. RS-232 interface, I used to solder the cables to connect these things to the server, and it used the TTY protocol. This was a laptop from the time with this tiny, tiny little monochrome LCD screen, 640K of RAM, because as Bill Gates said, who could possibly need more than that? And it weighed 6.4 kilos. It was a monster. Again, do not drop it on your foot. That cost about £6,000. Now we have things like the Lenovo ThinkPad X1 Extreme, which has it's insane. It's ridiculous. And it's much, much cheaper. And printers are brilliant as well. That's making a noise there. It's not making a noise for you. But yes, and then there were things in 1990 that just didn't exist. We just didn't have them. So the internet. I mean, the internet existed, but the World Wide Web, which is what everybody thinks of as the internet, didn't exist at all. If we didn't know what an error message meant, we had to figure it out or phone Infomix. It was weird. Obviously no Wi-Fi, because there was no internet for the Wi-Fi to work with. There was no such thing as the cloud. If you wanted a server, you went to purchasing people and went, I need a server, and then 6 months later, maybe you'd get one. We didn't have touchscreens, we didn't have mobile phones, honestly. 1990, I don't think I had my first mobile phone. I got my first mobile phone probably in 95, let alone the sort of supercomputers that we're all carrying around in our pockets now. This is from 1993. This is the Apple message pad, or the Newton. And this was Apple's first attempt at a kind of note-taking device, and it was shit. It sucked. And this weighed 640 grams, and it really wasn't very, very good at all. This is an Apple iPhone 16 Pro Max. It's got all the colors, 8 gigs of RAM, a terabyte of flash memory, and it weighs 227 grams, and it basically does everything. So, the progress that we have seen over those last 35 years, things have got faster, things have definitely got much smaller, things have got lighter, we can carry supercomputers around in our pockets, things have got preciser. I'm now mucking up the grammar because you can't do that with the word precise, but I'm doing it anyway. They've got powerfuler, because I've started, so I'm just going to carry on now, and they've got connecteder. Everything is connected to everything else. So my new hobby is extrapolation, taking what I've seen over the last 35 years, what can I predict for the next 35 years? And so if we extend Moore's law out to 2060, then we get to quadrillions of transistors. For various reasons, that's not going to work. And one of those is the fact that the process nodes literally can't get much smaller. 2025, the sort of current state of the art is 3 nanometer. TSMC are taping out 2 nanometer and 1.4 nanometer. But you get to this point where the things that the transistors that you're theoretically making are smaller than silicon atoms, which, no, you can't do that. It turns out that's not going to work. And so we're looking at other processor possibilities, like silicon germanium is what they've used to get to this point, the latest 3 nanometer and everything. That's a silicon germanium mix. We're looking at graphene, carbon nanotubes, that sort of thing. Photonic processors. So one of the reasons that we can't just make the chips bigger and sort of make the CPU cores bigger is because we are governed by the speed of light. And so you can't have the transistors being physically too far apart because the charge can't travel between them fast enough. It's not the speed of light, it's the speed of electricity in whatever it is. Photonic would enable you to make bigger transistors, but then we need to make things that emit and absorb light. And we're talking about individual photons. So that could be fun. Organic processors, we could just start farming monkeys and then sticking them together and calling them a Kubernetes cluster and running stuff on their brains. I'm thinking that might get some people angry, though. Is this application vegan? Yes. And then, of course, we've got quantum, and we'll be coming back to quantum a bit later on. But I will just whet your appetite with this. A 64-bit quantum computer, each register can hold, it's on the speaker notes, but I couldn't get the speaker notes to work. I can't remember how to say that. That's a big number. That's different value at the same time. Okay, we'll come back to that anyway. So, current trends, well, let's talk about the connectedness of things. This is a non-exhaustive list of things connected to the Wi-Fi in my house, which I wrote by going through the Deco app. 8 computers and phones and tablets, 2 Xboxes, a PlayStation, 2 Nintendo Switches. My kids are spoiled rotten. The TV is connected. 3 Sky Q boxes, 2 Amazon Fire TVs. My wristwatch connects to the Wi-Fi. There's a bunch of Echoes, some Kindles, all the light bulbs, the doorbell, the washing machine sends out an alert to say, I've finished doing your washing. It also plays a lovely tune, which you can hear all through the house anyway. The printer, that's connected to the Wi-Fi, my camera, and probably many, many other things as well. If you take out the things that you would consider to be computers, so the 8 computers, the 2 Xboxes, and the PlayStation, you're still left with a sort of big list of stuff here. But actually, all the stuff on the left, you can kind of go, I can see why that's connected. But the stuff on the right, these are not computers in any sense of the word that I would have understood in 1990. And all of these things are connected and talking to each other and interacting with each other. And the reason they can do this is because we've got low power devices like Raspberry Pis, Raspberry Pi Zeros. This is Raspberry Pi 5. That's the 02W, which has got Wi-Fi on board. This is the NVIDIA Jetson Nano Super, which I'm planning on getting one of these. This thing has got 1,024 ampere cores on it. That's the GPU cores from the 3090 series, possibly the 4090. And this thing will run AI inference workloads. It'll do speech recognition, speech synthesis, all these sorts of stuff. And it's just entirely local. And again, this is a low power device. It's based on ARM. It's based on NVIDIA's GPU cores. And there's other things as well that do that. And there's multiple reasons why this low power thing is important, though. And actually, I think the most important one is not that we can have lots of little things, not like the Internet of Things, where there's just crap all over the world, all sending stuff over MQTT protocol or whatever. It's the amount of electricity that we are using as an industry, as a percentage of all the electricity, of all the energy being used, is going up. And this graph is out of date because this graph was done before OpenAI and Anthropic and Google and everyone started training these LLMs. So I'm guessing this is probably getting up to the 25% point now. And so anything we can do to reduce that, if you can run your application on a 7-watt ARM CPU Raspberry Pi, rather than a big kind of 400-watt server blade sitting somewhere, then that's going to bring down energy use. And so that's something that everyone, I think, should be looking into. You can get ARM-based cloud instances on all of these clouds. You can also find smaller hosting providers who will do it, people like Scaleway and so on. And yeah, we have, I think, a moral, ethical responsibility to start trying to look to deploy stuff. And .NET obviously works very nicely on ARM. You can build ARM Docker images, you can run it on ARM Kubernetes clusters, and most of the stuff that you're talking to can also run on ARM, things like Redis and PostgreSQL, I think, now runs on ARM. By the way, if you've got kids and you want to get them into this sort of low-power device thing, Make Code Arcade, it's a Microsoft thing. It's absolutely fantastic. They can build games either using drag and drop or a JavaScript kind of subset, and then they can deploy that onto things like the BrainPad or the Adafruit PyGamer or PyBadge or the KittenBot Meowbit. This is all just excellent way of learning to code. But we need to, for a long time now, we haven't worried about performance because the computers just keep getting faster. And so we just go, hey, my application just got faster. No, Intel just released a new CPU. Your application just runs for we need to start thinking about how many resources we're using and writing more optimal code to be able to account for this. Okay, let's talk about things that we have today that are still in the very early stages and that we are hoping will get better. So, like user interface. So, for the entire time that I have been working in software development, my job is to make rectangles appear on a screen and allow somebody to interact with those rectangles. That's pretty much it. We are now at a point where that way of interacting with computers is going away. We've got computers we can talk to, and we've got a user interface that can surround us completely or be overlaid on the world around us in the sort of style of Ready Player One. And so we can all have avatars and look like this is what avatars should look like. And then you've got Mark Zuckerberg. So yes. But this is an Oculus Rift, I think, or possibly it's an HTC Vive, and that's like the absolute top-end, amazing VR kit. But it does have a lot of wires running from sort of controllers and everything else, and also it needs an extremely beefy computer to run it. But now we are actually getting to the point where they can build all of this directly into the headset, again using ARM processors and low-power processors. The Oculus Quest 3, I have one of these at home. It's got a battery thing that sticks on the back. It can go for 4 hours between charges, and you can also just have it plugged in while you're using it. And this thing, the graphics performance is similar to an Xbox One X. So it's not quite current generation, but it's still amazingly good when it's entirely surrounding you. It has a pass-through mode, but it's not what I would call usable for anything. It's not like an augmented reality thing. But we also have the Apple Vision Pro, which has extremely good pass-through and is designed to be worn for a very long time, like your entire workday. And this has incredibly high resolution. The field of view is very good, and this will overlay things on the world around you. And this is, I think, the direction that user interfaces are going to be going over the next few years. Is we'll lose the screens, we'll lose the keyboards and all this sort of stuff, and we will have applications will just be embedded in the world around us and ready for us to interact with them in a contextual way. And then to sort of do the comparison, if you look at what it took, it was 13 years from that 640-gram message pad with the pen and the monochrome screen to get to the original iPhone with the capacitive touch screen and tiny, tiny little thing and the entire power of the internet in your pocket. And so if we take that and we apply it to like augmented reality headsets, and Apple do the same kind of innovation and iteration over the next 13 years, I do think we are going to get to a point where you have a pair of glasses that you can just wear. And I mean, we're actually already there to a certain extent. So this is Nreal, and this is the Nreal Air glasses. And those are augmented reality glasses. Those work, those overlay things. There are issues around graphics quality. There are issues around the transparency of things and so forth. But we are going to get to this point where a lot of things could potentially become unnecessary if you've got a pair of glasses that can make it look like stuff is there. Like, why buy pictures and hang them on your walls when you could just program your walls to display different artists on different days? You go, oh, it's Friday, it's Van Gogh. So yes, I have two applications that I want to build when we achieve this level of augmented reality. One of them is a very simple one. You draw out a route on Google Maps, and then you go and run it with your augmented reality glasses on, and there's coins all the way along, and they're just going bing, 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 just to give you that extra motivation to keep running. Or you could have like just like round dots and then 4 colored ghosts chasing you. But then, with the money that I make from that, which obviously is going to be millions, I'm going to... Has anyone seen His Dark Materials or read the books? So yeah, the characters in these books, they have demons. They have it's their soul. It's external to their body, and it takes the form of an animal. And when you're a kid, you can it switches between different animals. And then when you hit adolescence, it sort of takes its final form. But these things, we talk about the sort of the external brain, your notebooks and Evernote or Obsidian or whatever, and with the combination of AI LLMs and conversational AI and then augmented reality, and you can basically program animals to interact with your surroundings, and we could all have a cute little animal just following us around everywhere, and that's our personal assistant, and you sort of wake up in the morning and it's just sitting there looking at you and you go, hey, what are we doing today? And it tells you. So yes. So I think that everybody who wants to be building applications, if this is where we're going, you need to start at least having a basic understanding of 3D graphics and modeling, spatial design, and these new interaction models, these voice interaction, just gestures and all this sort of thing. If you want to sort of use your existing C#.NET skills and start exploring some of this, you can check out Unity. It's free again. And it has AR support, so it will work with, I think they support the Apple Vision Pro. You can use it with the Quest 3 with the horrible grainy pass-through and everything. But yes, there's a bunch of stuff that you can use there. And if you want to look at this stuff on the web, then go and check out aframe.io and search for WebXR. These are the kind of web versions of these things. So instead of going to a web page, you'll enter into a web room and find Easter eggs or something. And Snow Crash is an excellent book. I recommend. It's got a really solid vision of what cyberspace could potentially be like in the future. All right, what's next? A blank slide. Oh yes, manufacturing. At the moment, we've got factories all over the place, and when I say all over the place, obviously, I mean China. And there are people in those factories, and they're going ka-chunk, 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 and all this sort of stuff. But we now have this new thing. We have 3D printing. In 1992, this £1 million machine, $100,000 machine, this was one of the first 3D printers, and this was incredibly expensive, and it was used for prototyping parts and all this sort of stuff. And then by 2007, students at the University of Bath had built the RepRap, the self-replicating 3D printer. So you could print all the plastic parts for this printer using the printer, and then make another one, and so on. And now you go onto Amazon and you search for 3D printer, and for £100 you can pick up something that you can connect to your computer, and it will print a boat. Once you've got the bed leveled and the right sort of PLA plastic hooked up and all that sort of thing. But you can get, like this is a nice easy one, the DaVinci Junior, comes fully assembled, just sets itself up out of the box, has Wi-Fi. This is the DaVinci Color, which uses special white filament and then literally adds ink to it as it is printing, and so it can print multicolor things like in the full spectrum of colors. We have this kind of laser-based thing where it's actually curing resin with a laser as it lifts up out of this pool of resin. Those things are really good. This is the current sort of what I would buy if I were buying a 3D printer today, Bambu Lab X1C. So it's got 4 filament rolls on it. I believe you can hook extra ones up as well. This thing is insane, and it can print incredibly fast. And you can print all these kind of gadgets. And it took 20 years for us to go from dot matrix printers, which were incredibly noisy and only 2 colors and couldn't do very much, to get to tiny little photo printers that will produce better photos than you used to get from Boots the Chemist when you took your negatives in to be developed. In the very near future, we are going to be able to 3D print gadgets. So if you can hook up enough materials to your 3D printer, then there's no reason at all why it can't print circuit boards and these kinds of gadgets. And so, I mean, that's from MIT, I believe, did this, and they printed a remote control. The only thing they didn't print was the batteries. And this is in a research lab, and it wasn't entirely just set it going and come back. They had to keep sort of switching different bits and pieces out, some assembly required. But in the very near future, we're already getting to the point where they can 3D print food. So you can put the proteins and various other things in, and you can print a steak. It tastes like shit, but you can print it and you can eat it, and it does have nutritional value. And so that's something, and they're still working on that. That's going to get better. So we will eventually get to the point of being able to say tea Earl Grey hot, and it will just be formed out of energy taken from dilithium crystals. The one thing stopping Star Trek from actually happening is that dilithium crystals are imaginary. Other than that, it's a really brilliant idea. Okay, let's talk about AI. I saw the talk, the first keynote talk was about collaborating with AI, and my job is going to be reduced to looking over an AI's shoulder to make sure it hasn't made any mistakes. Yeah, no, I'm not wild about that, to be honest with you. But it's here, and we need to talk about it. So let's do a quick history of artificial intelligence. In 1950, Alan Turing proposed the Turing test. If you can be in a room and having a conversation, and you think the person in the other room is real, then if it's a computer, it just passed the Turing test. We have blitzed way past that now. 1956, McCarthy and Minsky started the AI lab at MIT. In 1973, the Lighthill report came out and confidently asserted that computers would never be able to do more than an amateur chess player. So yes, in the 1980s we had expert systems. That was a dead end, Prolog and all those sorts of things, but those were clever. 1997, so 24 years after the Lighthill report, IBM's Deep Blue beat Garry Kasparov in a chess match, and Kasparov was not happy about that. 5 years after that, we got the Roomba, which will just pop out and hoover your house. Can't hoover my house, it's too messy, but other people's houses, apparently. Boston Dynamics are still out there and still building dogs, seem to be the thing at the moment. And you go, hey, that's a very, very cute dog. What have you put on the back of the dog? And they go, that's a General Electric N134 minigun. I don't like your dog anymore. In 2011, Watson, IBM's Watson, which is still their kind of main model that they work on for this kind of AI, it played Jeopardy, and it was listening to the questions, it was understanding the questions, it was finding the answer, and then it was formulating its answer in the form of a question, because obviously Jeopardy. And it won. It absolutely trashed the Jeopardy champions. We also got Siri in that year. Siri's been around for 14 years. Can you believe that? It's insane. Still rubbish, but it's been consistently rubbish for 14 years, and you've got to respect that. 2014, we got Alexa, same sort of thing. Amazon had such huge Alexa was basically, you're going to go, oh, we need toilet roll, and it would just overhear you and go, all right, I've ordered some toilet roll. All anybody ever uses Alexa for is playing music and setting timers. And I know that because that's, sorry? And turning on the lights. She's rubbish at that, just like explaining to her that you only want the top light of that sort of stuff. Anyway, 2014, we got driverless cars, Waymo, and all these sorts of things. Yeah, and that's going brilliantly. So I don't think we're ready for driverless cars yet. 2016, Google Assistant, late to the party. AlphaGo in 2016. So once Garry Kasparov had been beaten by Deep Blue, they went, oh, well, chess is finite. Go, no computer is ever going to be able to play Go. And then DeepMind came along in 2016. AlphaGo thrashed the current thing. And then there was AlphaZero, which they didn't even teach to play Go. They just made it play Go against AlphaGo, and AlphaZero worked it out from first principles, and then it could be AlphaGo and, by association, every Go player in the world. 2020, AlphaFold started solving the protein folding problem for us. That was something that we had protein folding at home because they needed all that extra CPU so that they could try different ways of folding proteins, and then AlphaFold came along and went, it's just like that. Yeah, thank you. And then, of course, in 2022, we got ChatGPT, which was the beginning of the end of the world. And that's thank you for coming to my TED Talk. No. We now have ChatGPT, we have Copilot, we have this thing that's sitting there. Honestly, I think once we get to the point, I don't like having to kind of move my cursor out of my editor window and into the Copilot thing and type questions. But once they get it hooked up to a microphone and I can just be talking while I'm working, that's a Copilot. That's what I want, is I can, or, you know, it can interrupt me and go, hey, what are you trying to do there? Because there might be a better way, you know? But if it's an actual conversation, like when I'm pairing, except with somebody competent. But the thing I want to say about AI, though, because we talk about, we're all going to lose our jobs because AI is going to take over and be able to build applications, and people going, oh, look at this React to-do application that I built with AI. And you're kind of going, how many swimming balls did you boil for this demo? But the bigger point here is that the AI is running on the computer, which is also where the information that we want is. And so why will we build applications to display information on screen in very sort of predefined ways, queries that we've thought our customers might want to run, operations that we think our customers might want to do? At the end of the day, all it is doing is taking user input, adjusting some kind of stored state, and then returning user output. And if you've got AI, you don't need applications. You can just tell the AI what you want to happen, and it will go and make it happen. And then if you want, you can go, can you just do me a table showing this, this, and this, and it will just generate it on the fly. So the idea that AIs are going to be used to write lines and lines of JavaScript or C# or Go or whatever, they're not. They're just going to replace all the sort of line of business applications anyway. They're not going to replace games and leisure stuff, but yes. Spotify could go away. You just go, AI, play some Taylor Swift. And it'll go, no, she's not on Spotify. We have neural processing units that are making all this stuff faster. I am seriously running out of time. We have AI as a service, and we have these SDKs, semantic kernel and everything, so you can get playing with those. Check out semantic kernel on Microsoft GitHub. Run it in .NET 9. This lets you interact with all the AI services on Azure and Anthropic and all these other things. It's kind of like an SDK for AI. So let's talk about the future. Quantum computing. Quantum computing has just had a really big boost, so I was going to leave it out, but I've put it back in again. We have 3 types of quantum computing. We have a quantum annealer, which basically just proves that quantum computers work. Then we have analog quantum, which is where we can model other quantum processes, like the way nitrogen binds to the roots of plants. And if we can actually figure out how the hell that happens, then it would make fertilizer a lot cheaper, a lot more efficient, and a lot less destructive. And the green lines are on this as well. That's a weird thing. Where we want to get to is universal quantum, where the stuff that we're using normal processors for at the moment, we can do on quantum computers instead in a fraction of the time. And as far as I can understand, by the way these work is that it runs your program in all the universes at the same time, and then the one that got the right answer shares it with all the other universes. That is seriously the many worlds interpretation of quantum mechanics, is how they think quantum computers work. They know they do work, they've tested them, they definitely work, we don't know how, we think it's the multiverse. Stephen Strange is now in charge of computers. And Microsoft have just announced this. This is the Majorana 1. This is a topological core quantum processor which has its error correction built into each qubit. So the qubit looks like this weird thing, and at one end you've got a proton and a neutron, and at the other end you've got an electron, and then that can be in, that counts as a qubit. That one of those 64 of them, and you can store all those hundreds of quintillions of states. So yes, this is designed so that they will be able to fit 1 million of them on a normal-sized computer chip. Currently, they've managed 8. But apply Moore's law, speed it up a bit, double that, we will get to 1 million on a chip really quite quickly. And then cryptography is screwed. We'll be able to crack. The NSA will be able to read all that encrypted data they've been storing under Utah for the last 50 years and find out what people have been talking about. Oh, we could have stopped it. So yes. But if you want to look into the quantum stuff, go and check out Microsoft Quantum Development. Q-Sharp is their language for doing quantum stuff. As far as I can tell, you go, here's some data, H-gate, here's the answer. It's magic. I have no idea. And then there's nanotechnology. This I am excited about. So this is kind of related to the 3D printing. But this is the kind of what we can do with these tiny little materials and things. And so we have nanomaterials like carbon nanotubes and nanoparticles and quantum dots and new kinds of medicine where they're building tiny, tiny little machines that just go in and attach to cancer cells and destroy them, which is completely insane. We're looking at, so the way Microsoft build the Majorana 1 chip, you can't like get a pair of tweezers and put a qubit on the chip. You have to set it up so that the qubit occurs spontaneously on the chip. It's incredibly weird. Once they've got it up to like 1,024 qubits on a chip, they'll be able to use that to simulate the process of creating the chip, which will then enable them to improve that further. But yes, we're looking at using kind of DNA and RNA style, but constructing it ourselves. And then top down, we got EUV lithography and solid state systems and focused ion beams and all this sort of stuff. And then, I mean, everybody knows about anisotropic superparamagnetic materials, but they are exciting. I have no idea what they are. But yes, we've got molecules that are just single molecules, things that a chemist would go, that is a single molecule, but it's actually a tiny little machine. And biomimetics, so we're looking at nature like the thing with the nitrogen and plants and everything. We can look at nature, go, how is nature doing that? Because it's been really efficient for the last 3 billion years. And then there's speculative stuff, being able to manipulate molecules, nanorobotics, and all this sort of thing. If you want to get started in this, you'll need a bachelor's degree, a master's degree, a PhD, and a research position at a good university. So I'd start on that now. I'm going to recommend another Neil Stephenson book, though. This is the best kind of speculative fiction about what nanotechnology could look like in the very near future. By very near, I mean by 2060. That's all assuming that we survive the various asteroids that are going to be passing by Earth. And honestly, is anyone else, you know the one that's going by in 2028? Has anyone else got their fingers crossed that it hits the White House? That would be, that would just be God going, no, stop it. This is Apophis. Apophis is going past in 2029. Honestly, if things don't start getting better, I'm actually going to build a giant magnet and just pull it down and just go, yeah, no, start again. But assuming that doesn't happen, by 2039, we could be building colonies on the moon, on Mars, building sort of large habitats around the solar system and everything else. And if we do make it to 2060, the AIs will be running everything. They won't need anybody looking over their shoulder or collaborating with them. They will be wise and beneficent, and we will have 100% leisure time to create art and commune with each other and do philosophy and live with our extending arms and our robot dogs, all watched over by machines of loving grace. That is my little talk. Thank you for coming to it, and I will be around for the rest of the conference if anyone wants to talk about things. Thank you.